Good morning. My purpose is to provide a background for a series of treatments of global ecological change and of the kinds of public policy responses that we're going to require in order to deal with it. You will see those lectures forming the main part of the schedule in B for the rest of the quarter, and this happens to be a B lecture. Those of you who woke up 3 minutes ago can be forgiven for not understanding that, but if you'll consult your schedule, this is the time where B precedes A out of the normal order. Now, there have been two thematic concepts in this course so far. One of them is the idea of homeostasis, what it is that keeps a system stable in the face of imposed change, what kinds of regulatory responses cells, organisms, even whole ecosystems have to external perturbation. The second theme, predominating in the B series, has had to do with conflict and conflict resolution. How do we design institutions to do that? What sorts of conflicts are we good at resolving and what not? To what extent does what we learn about conflict resolution in the behavioral context between individuals affect the wise design of national or transnational policies in the face of conflict? I think those concepts apply very well to the subject matter that we're beginning to work on today. And I want to begin by seeing if we can do any good applying the idea of homeostasis to this small planet of ours. Historically, that's been a very difficult thing to do. I suspect that people who have pondered the immensity of the Earth and understanding Earth systems, by which I mean geology, the formation of major ecosystems, the circulation of the great ocean basins, the sweep of weather across the surface of the globe, have simply given up because it's too big to see from here. But we now have a different perspective, and I think that perspective is perhaps best symbolized by the new views of Earth brought back to us by space travelers. The great British astronomer Fred Hoyle, the originator of the Big Bang theory, said in 1948, back when space travel was still the stuff of science fiction and not contemporary reality, he said, once a photograph of the Earth taken from the outside is available, a new idea as powerful as any in history will have been let loose. And I think that's true. We've all seen it and experienced the kind of revision of perspective that seeing that blue, partly cloud-covered globe from the distance of the moon or some great part of the system of oceans and land masses from a high-orbiting Earth satellite, understand what that revision of perspective is. But the most powerfully affected people have been the space travelers themselves, not a one of whom has not come back with a very different view of the world. Americans and Russians, for once, appear to react in exactly the same way. Here is astronaut James Irwin. He says, that beautiful, warm, living object looked so fragile, so delicate, that if you touched it with a finger, it would crumble and fall apart. And now here is cosmonaut Vladimir Kovalyanok. He says, after an orange cloud formed as the result of a dust storm over the Sahara and caught up by air currents, finally reached the Philippines and settled there with rain, I understood that we are all sailing in the same boat. When you think about it, that really is an extraordinary altering experience, to think about the Earth as a seamless place, to think about it as a global environment in which everyone has an equivalent stake, in which all nations will survive or not survive together. Now, why is it that way? What basic rules, scientific rules, govern the unity of Earth systems? They're pretty hard to summarize in a lecture, and later on from my colleagues you will hear much more detailed dispositions of almost every one of the aspects I plan to summarize this morning. But I think it will be useful to give you an elementary roadmap to use in thinking about these problems and to employ in developing for yourself this basic idea of the unity of Earth systems and the indivisibility of the fate of this planet. Let's begin with some very fundamental thermodynamics. There are a few energy inputs that are contained within the Earth. They arise from the fact that the core of the Earth is hot and that heat can escape from time to time and place to place as geothermal energy, as underwater plumes of hot water that it turns out now develop their own little ecosystems of organisms that do well under those circumstances. But by far the greatest energy input, of course, is in the form of sunlight. And by sunlight we also mean sun heat, because the solar radiation exists in a broad band of wavelengths and energies, some of which we use to see and plants use to photosynthesize, but some of which are very much longer wavelengths of lower energy that are useful primarily in terms of heating. So we can divide that input actually into two different components with quite differential effects on global thermodynamics. One of them is energy in the form of heat. The other, energy in a form that can do useful chemical work. And the primary chemical reaction that traps that energy on Earth and powers all of the rest of the biology of the Earth is the process of photosynthesis. Consider every useful energy yielding reaction that is employed by living organisms. It derives in one way or another from this kind of energy. Some of it, of course, is produced in near-time cycles. We employ the energy of photosynthesis in the growing of crops, and that provides the basic yield that is the basic stuff of human consumption and indeed of support for all of animal life. Growth derived from photosynthesis also produced in historical time organic material that over geologic time was trapped and chemically changed and formed into fossil fuels. So real-time photosynthesis yields the basis of the pyramid of biological productivity on which all living systems depend, and historical time photosynthesis yields the fossil fuels with which modern industrial societies are powered. Now, of course, the combustion of fossil fuels and the combustion of stored carbohydrate or fat or protein in a living organism are processes that are fundamentally similar. They involve the oxidation of compounds containing hydrogen and oxygen and carbon to yield carbon dioxide and water. That is just as true if you are talking about an animal as it is if you are talking about an internal combustion engine, although the chemistry of the substrates is a little bit different. So all of the energetic reactions that take place on the face of the Earth yield carbon dioxide. All of them use oxygen, except, of course, for photosynthesis, which powers all of this by doing exactly the reverse, that is, by fixing carbon dioxide and by producing oxygen. In that sense, not in the details of the biochemistry, but in that overall energetic sense, photosynthesis is the reverse of respiration. So if you think about this in terms of a cornfield or an ocean, here's what it means, and I think this is a useful notion to carry around with you. By day, a cornfield is actively photosynthesizing, fixing carbon dioxide in the form of energy-rich molecules, giving off oxygen. At night, that same cornfield is respiring, that is, it's exploiting those materials that it has built up during the day by the process of respiration, and it is producing carbon dioxide instead of fixing it and using oxygen in the process. Now, whether there is a net fixation of carbon or a net production of carbon in the form of carbon dioxide depends entirely on what the plants are doing. If they are growing rapidly, adding mass, adding energy over time, it means that the amount of photosynthesis accomplished during the day considerably exceeds the amount of respiration done at night. There is therefore what we call net production, and more stored energy is available for human consumption or for burning or whatever. Please note that by this account, a mature, stable forest, which isn't growing very much, is not fixing very much carbon on a net basis, whereas an agricultural crop, which the farmer has arranged to grow like hell, is fixing a good deal of carbon on a net production basis. In the ocean, where well over 3/4 of the photosynthesis accomplished on this planet is done by single-celled algae, if these algae float near the surface where the light is bright, they grow and multiply rapidly, and their photosynthetic rate vastly exceeds their respiration. At the bottom of the ocean, if they sink down there where there is very little light, inevitably respiration will exceed photosynthesis. And oceanographers regularly refer to the point at which photosynthesis exactly balances respiration so that it zeroes out as the compensation depth, the point at which the plants are, so to speak, in neutral with respect to the fixation of carbon. Well, why spend so much time on the photosynthetic aspect of the Earth's energy budget? Because the carbon cycle, even though carbon only constitutes less than 1/10 of 1%, less than 1/20th of 1% of the gases in the Earth's atmosphere, it is a very important gas, now more than ever, because of the greenhouse effect. certain gases contained in the Earth's atmosphere, of which carbon dioxide is one but not the only one, have the property of permitting most of the high energy visible region of the sun's emission spectrum to reach the Earth. They are transparent to it, but they absorb or re-radiate long wavelength radiation, heat, which is otherwise tending to be lost from the Earth to the cold, dark well of the outer atmosphere all the time. Thus, the greenhouse gases of the atmosphere trap heat in much the same way that a greenhouse does, and without these gases, the Earth's surface temperature would be vastly lower than we actually find it. I'm going to speak in a moment about the well-publicized effects of changes in atmospheric carbon dioxide on the greenhouse effect, but you need to know that it is a complicated story about which the data aren't all in. There are other important greenhouse gases beside carbon dioxide. Methane, which is a gas of largely biological origin and which is a product of a minor product of certain kinds of agricultural activity, is a significant greenhouse gas. So, much more importantly is water vapor. And that, by the way, is one of the issues that makes the whole greenhouse effect problem a difficult one to model. To the extent that the initial warming of the Earth caused by more carbon dioxide in the atmospheric greenhouse, to the extent that that initial warming produces more evaporation of water from the oceans and thus more water vapor, the greenhouse effect is accelerated. And there is thus a kind of positive feedback between the addition of carbon dioxide and the subsequent addition of water vapor. Nobody knows exactly what the right interaction term is to apply to that synergism in modeling the greenhouse effect. One doesn't know exactly what to do either with the fact that the global warming associated with the greenhouse effect, predicted to occur as a result of it, will be differential as between the equator and higher latitudes, so it's likely to drive significant changes in weather patterns, and that too is an unpredictable aspect of the modeling so far. Of course, the heating of the Earth does something else too, and it's important to recognize it, if only to recognize it. There isn't time for a treatment that's at all exhaustive. But remember that the heating of the Earth by the sun is not the same at all latitudes, and that temperature differentials set up by that fact drive the great weather systems of the world. They drive the circulation patterns of they plus the natural rotation of the Earth drive the great circulation patterns of the ocean basins, which are clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And that has profound effects on the conditions for life on the major land masses of the world. It sets up a pattern in which rainfall moves in storms from west to east across the continent of North America, and that in turn determines where plants can be grown commercially. It's what makes the Great Basin and the high deserts of the Southwest arid. It's what makes the increasing rainfall pattern as one goes across the Great Plains from the west, primarily cattle grazing area, to the east, the old tall grass prairie of the pioneers, where now corn and soybeans are grown. So the great heat engine of the sun, coupled with the rotation of the Earth, produces just a majestic pattern of water circulation and of consequent wind and weather movement that has much to say about how life cloaks the land masses of the Earth. One of the sad things about contemporary life, I think, is that we don't have the old course anymore called physical geography, which talked about human settlement and human agricultural patterns in terms of these great climatic systems. It's one of the things that I hope can be restored in another guise if we ever get to teach a three-quarter course on Earth systems science, but that's another story. An important element in the reaching of energy to the Earth from sunlight, and I want to make sure I get all the well-publicized things out on the board, is the ozone layer. And that plays a significant role because ozone is notably opaque, not transparent, to some important wavelengths of sunlight that are otherwise damaging. The shorter wavelength ultraviolet part of the spectrum, higher energies, shorter wavelengths than you and I can see, although they probably produce a little fluorescence in our lens, so that if you got exposed to a big shot of such light, you might see a bluish haze for a moment. But by and large, these wavelengths of light are beyond the human visible spectrum. But ultraviolet B light is abiotic. That is, it is inherently damaging to biological tissues if it reaches them. Probably because it produces direct changes in the nucleic acids that constitute the primary hereditary material of cells. And so the integrity of the ozone layer is a very important matter. Now, one is beginning to recognize the significance of all of these things scientifically. It wasn't until the early to middle 70s that it was understood, I think the first paper was in 1973 or so, that it was understood that certain compounds were capable of attacking and destroying ozone, inert gases, or previously thought to be inert gases, that are very persistent and stable, and when they reach the upper atmosphere have the effect of destroying ozone. Prominent among these were a set of compounds called chlorofluorocarbons, CFCs for short, which have been used in various refrigeration applications quite widely, but also as aerosol propellants in various kinds of consumer goods, hairsprays, cosmetic sprays of various kinds, and so forth. When I was first commissioner of the Food and Drug Administration in 1977, we actually signed collaboratively between the FDA, the Environmental Protection Agency, and the Consumer Product Safety Commission a regulation banning the use of chlorofluorocarbons as aerosol propellants. That regulation was interesting because it was the first time in all of human history that a substance suspected of global harm was actually regulated before a demonstration of the effect on a kind of worldwide basis. Simply the demonstration that it could happen, the known data on chlorofluorocarbon release, known data on the integrity of the ozone layer, were enough to convince everybody that the risk was simply too great to take. You know now that there have been important sequelae at the international level. The President told the National Academy of Sciences 2 months ago that scientific advances had made us aware of the damage to our Earth's protective ozone layer and the need to reduce CFCs that deplete our precious upper atmospheric resources. After an amount of waffling that some of us thought was unfortunate, President Bush has in fact asked the U.S. and its representative, who is the new EPA Administrator, William Riley, to take the position that there should be worldwide elimination of chlorofluorocarbons by the year 2000, provided that safe substitutes are available. I shouldn't have thought that for most of the applications the proviso was even necessary. But the basic outcome is good news, and there will be international action to restrict chlorofluorocarbon use progressively during the 1990s. That is surely good news. The current news on other aspects of the problem is perhaps not quite so good. The evidence from historic data, I think, are quite clear that global warming resulting from the addition particularly of CO2, but perhaps also of other greenhouse gases, has already been observed. And that the 30 years between 1959 and 1989 were on the average about a half a centigrade degree warmer than the 30-year period of about 100 years before. It is doubtless premature to place the blame for the American drought of the past 2 summers on global warming. After all, if you look at the record of climatic temperature changes over the past 100 years, it's very spiky. There's a wide, noisy variation from year to year. But it's quite unmistakable that the trend line has moved upward. I doubt that were it not for that upward movement of the baseline, we would have been in the situation we found ourselves in last year when, for the first time in memory, certainly in post-war memory, the United States was a net importer of grain. We are used to thinking of ourselves as the granary of the world, as the biggest agricultural exporter of the world. Last summer, we were negative with respect to grain on an import-export basis. The projections for the next 100 years are indeed considerably more alarming, because with the world's population growing at the rate it is, and with many less developed industrial economies contemplating conversion, there can only be an increase in the use of various fossil fuel energy sources, and it's a problem that we need to cope with. It is worse because of thermodynamic limitations that we must live with. Recall that energy lost through the combustion of fossil fuels cannot be regained. Any organism, or including man, burning a sugar, or man burning an organic fossil fuel equivalent, the energy that's dissipated as heat cannot be reorganized into useful chemical form. So one has produced some warming in the short term. One has lost some energy that is essentially unrecoverable, and it is from a source that is being renewed at a much slower rate than it's being used. So it is really a permanent loss. And it adds carbon dioxide to the atmosphere, which has its own secondary effect on global warming. So that is a major feature of of human utilization of these stored reserves, and it is a substantial problem. Let me put it in perspective in the following way. We're very concerned at the burning of tropical forest for all kinds of reasons, and I think most of them are good reasons. We are concerned because it represents a loss of species to science and to those of us who appreciate biological diversity, because it represents the loss of a valuable resource to people in those parts of the world. Finally, because it is adding smoke and carbon, other pollutants and carbon dioxide to the atmospheric greenhouse. But it must be recognized when industrial nations turn to developing nations and say, don't burn your forests because it is adding carbon dioxide to the atmosphere, that it is perfectly legitimate for those developing nations to turn back to the industrial nations and say, yes, but your per capita fuel consumption, energy consumption, is so much higher than ours that the difference associated with your excess development dwarfs the component that's being added by our deforestation activity, and that is in fact true. The amount of carbon dioxide contributed to the atmospheric greenhouse by the operation of industrial systems in the developed nations is very much larger than that added by the sum total of forest burning in the developing countries. Well, all of that, I think, can be understood as a loss of homeostasis. After all, homeostasis implies an equilibrium between what is used and what is added. It implies a kind of buffering capacity whereby the earth is rendered protected against imposed perturbations. It's not the only loss that we are experiencing. The great hydrologic cycle that's powered by the differential heating of the earth and the weather systems has produced in many places on land deep stores of water called aquifers. These are added to only slowly by annual rainfall. They represent accumulations from the past that are in their own way as non-renewable as the stores of oil that are held in similar reservoirs. There is the quality of water deteriorating in many places because of acid rain owing to the burning of high sulfur coal. Lots of topsoil gone because of overly aggressive agricultural practices. So all of these represent the loss of non-renewable resources accumulated as a result of processes on a geological time scale, but now being consumed on the basis of a human time scale, a problem surely for all of us. And the conflict between nations, as I see it developing in the 21st century, is going to have much more to do with the distribution of resources and the differential use of resources than the kinds of conflicts that we have been experiencing in the past. Let me turn now to get you to reflect for a moment on the kinds of worries in the field of international relations that we've had for most of the 20th century. For most of it, international security has been understood primarily in terms of international balances of power between great industrial nations. And for the last half of the century, certainly, that view of the world has been dominated by a contest, as it were, between the communist world, especially the Soviet Union, and the Western democracies, especially the United States. For all that time, starting with the Cold War, going through various versions of détente and so forth, and finally now to glasnost and perestroika, our descriptions of the state of the world have focused very heavily on the description of U.S.-Soviet relations. And our attention to that issue, of course, has been magnified by the terrifying knowledge of the extent of nuclear arsenals that have been maintained in both countries. Now, obviously, it would be premature to say that that fear is fading fast, but I think it is fading somewhat. I think its attenuation has been sparked in part by what are plainly new attitudes in the Soviet Union, in part by the eagerness of all of us to get on with arms control and disarmament, in part by what is perceived in many parts of the world, I think, as a pretty complete failure of the centrally managed socialist economies as economies, and a concern that the idea of spreading that to the rest of the world doesn't have a lot of steam behind it anymore. For a whole variety of reasons, in short, I think that the great power conflicts, the balance of terror, will no longer continue to dominate international relations in the 21st century, but rather that they will be replaced by a new set of concerns that are much more multilateral, include a much larger number of players, states that previously had not much hope of influencing world affairs, but which now have substantial capacity to do so. And what will drive those desires? Well, not only do we have the astronaut's view of the shrinking world with its failing homeostasis and its great unity, we've also got the television view that people in the developing nations have of the nations that are very much better off. It is increasingly being understood that a child born in the United States will, over its lifetime, lay claim to about 30 times the amount of non-renewable resources on this planet as a child born in, say, Bangladesh. As that difference becomes more apparent, as the desires of the developing nations become more focused and are triggered by more awareness of what life is like in other places, I think that those differences in resources will become less acceptable. Now, in the 20th century, there were differences of that kind. They had to do with resources that developed countries needed, and so they went out and got them in one way or another. And the bargaining power held by the developing world was much restricted. Only in a few rather special cases, like the organization of the petroleum exporting companies into a cartel that managed occasional price control, has there been any effective clout on the side of the developing nations. But I believe that the awareness of the global character of the environment will change these power relationships profoundly. We are already seeing the beginnings of it, just the very barest beginnings. Developed countries like the United States are now organizing swaps whereby they persuade developing countries to alter their conservation practices in return for forgiving substantial amounts of national debt on the part of those countries. The so-called debt for nature swap is becoming now a commonplace activity. It would not even astonish me if at some point in the 21st century one found a group of people sitting down at a table and finally, after long conversations and negotiations, agreeing to a treaty whereby one group of countries agreed to a series of steps to bring the birth rate below a particular level, in return for which another group of countries would agree to a series of descending caps on per capita consumption of fossil fuels. In other words, the new awareness of differential resource utilization in the world is increasing at such a high rate and is already so well developed that I think these forms of negotiation over the condition of the planet we all share may well come into being. In any event, it's clear that the developed world, the industrial world, cannot simply turn to a developing country that is burning its forest, like Brazil, and say, stop that. You're making the world less safe for all of us. Because the answer is that to make the world really safe for all of us, lots of countries are going to have to do some de-development. Lots of countries are going to have to agree to controls on their population growth rates that would have seemed quite inconceivable even 15 or 20 years ago. And there is going to have to be widespread recognition that, as the Russian cosmonaut said, we are all sailing on the same boat. That's going to be a profound equalizer of power among the rich and poor nations, among the nations that tend to fix more carbon dioxide than they produce, as well as the nations that produce more carbon dioxide than they fix. So I think it's a safe prediction that the theme of 21st century conflict resolution will likely be population, resources, and environment, not the bomb, not the survival of a communist system versus a capitalist system, but a very complex, multiple set of negotiations and arrangements among rich and poor countries that result in a more equitable distribution of the Earth's resources and some mutual agreements about the rate at which we can collectively afford to exploit them. The alternative, I'm afraid, is too unpleasant to contemplate for our children. I hope very much that people in institutions like Stanford will devote a lot of time to thinking about that problem, because it strikes me as compellingly significant. If we can't do a good job at persuading people that it needs to be attacked, I mean attacked with all the wisdom that we can bring to it, with good understanding of other cultures and other values, because we'll have to have that. A good understanding of global homeostasis, because if you don't understand the scientific base of that, you can't really work your way through the problem. And a good understanding of what it takes patiently to negotiate a resolution between what strike me now as almost impossibly difficult conflicts between national interest. Thank you very much.